Hello and welcome to today's ESA Hangout on Venus Express and the spacecraft's dive into the planet's atmosphere. My name is Emily Baldwin. I'm an ESA space science editor and writer based here at ESTEC, ESA's Space Research and Technology Centre in the Netherlands. Sat here beside me is Håkan Svedhem, Venus Express project scientist, and I'd also like to now introduce the rest of our guests. So at ESOC, ESA's Space Operations and Spacecraft Centre, we have Adam Williams, one of our spacecraft operations managers. Hi, Adam.
Hello.
And in ESAC, in ESA's Space Astronomy Centre near Madrid in Spain, we have Patrick Martin, Venus Express mission manager. Hi, Patrick.
Hello, everybody. Nice to be here.
And last but not least, we have Colin Wilson, and he is a Venus Express Science Operations Coordinator, and he is joining us from Oxford University in the UK today. Thanks for joining, Colin.
Thanks. Hi.
Also working in the background are my colleagues Erica Rolfe and Maria Bennett. They'll be collecting your questions ready to pass to me for the second half of today's programme. So just a reminder that you can post them in Twitter using the hashtag #SurfVenus, and you can also put them directly into the Google Plus environment. So I'd like to start today's Hangout by asking Håkan for a quick introduction to Venus Express itself, and more importantly, perhaps, why Venus?
Yeah, thank you, Emily. Venus, of course, is maybe the most interesting planet outside our own Earth, just because it's very similar to our own Earth and still so different. And just that particular thing is why we find it so interesting. So we have now Venus Express, this European Space Agency spacecraft orbiting Venus since 2006, and we've been collecting a huge amount of data since then. Actually, more than all other spacecraft together have collected in all those years before we arrived there. And we have been learning a lot, and we also been learning a lot about what we still need to learn. But indeed, there is very much data we have collected on Venus Express.
And we've been in orbit around Venus for 8 years. In those 8 years, what has stood out to you as being some of the highlights from the scientific return of the mission?
I think one of the most striking things is the variability in many of the different parameters we are looking at. The long-term variation and the short-term variation is much larger than we had expected. We can look at things like the winds, the global winds around the planet, what's called the super-rotating winds, very high-velocity winds. They were 300 km/h when you arrived, and we now see them at 400 km/h. Amazing increase that we can't explain.
And if I just pick up on the topic of the atmosphere, because that, of course, is the main theme for today's Hangout, we haven't just been observing the planet from above, but we've also been dipping the spacecraft a little bit into the planet's atmosphere. And I'd like to pass over to Patrick, if I may, to briefly explain what aerobraking is and why do we want to do it.
Well, very briefly, aerobraking is a technique that is typically used to circularize an orbit. And on Venus Express, we have actually a very elliptical orbit with the apocenter around 66,000 kilometers and the pericenter around 200 or so kilometers. So the idea for doing aerobraking on Venus Express, we could have done it a couple of years ago to really reduce the orbital period by a number of hours. But as this is also a risky operations, we decided to do it towards the end of the mission. And as Venus Express is running slowly out of fuel, we decided to do it now, basically. And so what we are doing is reducing the orbital period by up to an hour with the technique we are using now. Which is working really well, by the way. And of course, we are learning as well in terms of operations knowledge for future missions to do aerobraking on other missions, such as at Mars. But also, we are learning from aerobraking in scientific terms, and I'm sure Håkan and Colin will mention these such criteria. So in the past, we have been doing aerodrag techniques at 165 kilometers altitude, working really well, and now we are going much deeper in altitude with this aerobraking. And I don't know if Adam maybe wants to add some technical terms about this.
Yeah, Adam, perhaps you could talk us through this particular aerobraking campaign. When did it start? Whereabouts are we?
Okay, sure, Emily. So, as Patrick mentioned, our pericenter, which is the lowest point of the orbit, is usually at around about 200 kilometers or more. And we started this campaign by having what was called the walk-in period, where we just let the pericenter decline naturally, because normally it falls between 1 and 5 kilometers per day. So on the 18th of May, we let that continue, and we went below 200 kilometers. And eventually, around about the 18th of June, we got down to about 135 kilometers just by natural decline. And then we reached a point which is called the plateau, when the gravitational attraction of the Sun balances this natural decline, and so our pericenter altitude remains roughly constant. And this is where we do our aerobraking experiment, because we can be at the same altitude for several days at a time. And that goes on now until this coming Friday, when we reach the end of the plateau.
And a question that I've been asking you all week: what's the lowest altitude that we're going to get to during this?
The lowest altitude will be on Saturday, when we reach 129.1 kilometers.
Awesome. And Colin, we've talked a little bit already about the benefits of aerobraking from an operational point of view. What science can be done during aerobraking? Can we learn anything about the Venus atmosphere at the same time?
So until now, we've been focusing mainly on the lower atmosphere, the atmosphere above the clouds, the atmosphere below the clouds. But aerobraking takes us into the very top edge of the atmosphere, where the atmosphere reaches space, where it's the edge of the atmosphere, the edge of space. And this is really interesting, because this is where atmospheric escape happens. This is where components, the constituents of the atmosphere, are lost to space. So we think that Mars and Venus and Earth both used to have lots of water. On Earth we still have oceans of water. On Mars it's a lot frozen, but on Venus Express that escapes from the edge of atmosphere into space. And by understanding density variations and so on at the edge of the atmosphere, we can try to get more information on how that happens. So we're not using the pointing instruments, we're not using the cameras, the spectrometers and so on during this aerobraking period, but things like the magnetometer, which measures the magnetic field of Venus, and instruments measuring neutral particle abundances and ion abundances are still operating, and they're giving us very valuable information in this region.
So I'm going to ask Adam this question. What happens now? So we're in the last week of the aerobraking. Where do we go from here? And already Patrick mentioned about the fuel being near the end of its lifetime. What happens if we run out of fuel?
Okay, well, what we're going to do on Saturday is we're going to start to raise the pericenter, because if we didn't do anything, we would very rapidly descend out of control to the planet. So we're going to try and raise the pericenter. We have to do it in steps because of constraints on, as you say, the amount of fuel we have left in the tanks. We will do 15 maneuvers, one a day, and that will raise the pericenter then to 465 kilometers roughly. Well, we reckon that we have we have two components of propellant. We have fuel, around about 3 kilograms left, and oxidizer, which is around about 4 kilograms. And we need about 2.5 of one and 3.5 of the other to do the raising. So we hope that we get to the top of that maneuver, but there's some uncertainty on how much fuel we've got left. So it could be that we don't manage to do that raising maneuver successfully.
But if you get all the way up to the top, then what happens?
Then we will have a stable orbit, and we will then resume pointing experiments with the other instruments, and we try and continue the science mission. We no longer, of course, have a 24-hour orbit. We did 8 years of science where every orbit was 24 hours long. Now the orbit changes every day by an hour or more, so that makes our operations quite a bit more complicated, but we will work within those constraints as best we can to try and operate the instruments for as long as we can until we run out of fuel.
And is it a 24-hour job, babysitting a spacecraft when it's aerobraking, or how does it affect your daily operational life?
Well, it's not 24 hours, fortunately, because we only see the spacecraft for a number of hours per day, and we're fortunate that the communication passes for Venus Express fall during the day. They start around about 6 in the morning, and at the moment we run until about 8 in the evening. So it's quite convenient from a working point of view.
I think that's kind of given us a really nice overview of where we are today with the aerobraking. I'm going to move over to some questions now that I see have been coming in. Just a quick reminder to our viewers that you can just keep on posting your questions into G+ or via Twitter on Surf Venus. A question from G+ via Ian Constantine. He asked, is today the end of the mission? I guess that part of the question's already been answered, but he says, will the spacecraft be crushed? And I'm not sure who would like to answer that question. Adam?
Okay. No, I mean the pressures which we're experiencing from the atmosphere are not sufficient to do structural damage to the spacecraft. We're probably at most half the pressure that we would need before we saw structural damage at this stage. So no, we're not going to be crushed in the atmosphere.
And
only afterwards.
Only afterwards.
Yeah.
Well.
Another mission.
Eventually we descend to the planet, and then we get crushed then for sure.
We can't probably get burnt up before we get crushed by all the heating. But we're coming into the atmosphere at 10 kilometers a second, so that'd probably burn up the spacecraft before it gets crushed, I'd suggest.
And how long would you be able to monitor the spacecraft during the descent through the atmosphere until you lost the signal, if it was working and you could receive a signal?
That's difficult to say, but I think if we'd have gone down now from where we are at 129 kilometers, probably 3 or 4 days or a week, and then I think we would have lost contact with it anyway.
Kevin Burns on G+ says, congratulations on the 3,000th pericenter pass. How many more passes or planned estimated passes before the end of the mission?
Well, I think from a planning point of view, we're planning forward to mid-December. So if we have enough fuel to get to them, we have plans in place to take us through to around about the 20th of December.
Okay. Some science questions as well. Håkan, this is from Tanya Glittenberg. What are your wildest hopes to find underneath the cloud cover? Oceans or active volcanoes?
Well, we're pretty sure there are no oceans in the sense of Earth-like oceans of water or so, but we really do think that there are active volcanoes, and to have the real evidence of that is, of course, a very good thing to get. We've got very good indications in many respects. We've got increases of sulfuric dioxide at short intervals. We have seen heated areas on the surface with our infrared cameras that look down onto the surface, and these places, they tend to get warm and then cool off quickly in just a few days. So we think we have good evidence, but of course to see a really erupting volcano in real time, that would be a great thing.
What would you need to be able to see an active volcano that maybe you wouldn't be able to with the equipment on BEX?
No, I think we have reached almost as much as we can with Venus Express now in terms of getting science out of it during these 8 years. But if you look into the future, there are new missions that may include balloons that will circle down at a much lower altitude, or even landers that go down on the surface. Those will be the idea, in particular landers, because the visibility down there is not that good. You can only see a few kilometers. You will really need to be down on the surface to see the volcanoes.
Mm. And Colin, you mentioned earlier offline you've been studying future Venus missions. This ties in nicely with what Håkan was just saying, and also a question from Claudia Tanzanelia. After Venus Express is gone, does ESA have any plans for future exploration of Venus?
Well, not currently, no, but there's no shortage of new proposals for more missions. So probably the two leading candidates for future Venus missions being considered within Europe. One would be a balloon mission, as mentioned by Håkan, The advantage there is that instead of trying to survive at the surface where it's 450 degrees, you can instead survive in the cloud layer 50 kilometers above the surface where it's about 20 degrees, so very much a shirt sleeves environment, although you'd need oxygen and so on if you were to go there yourself. But you wouldn't need a pressure suit, you wouldn't need insulation and so on. So the sulfuric acid wouldn't be too great either. But hey, still, we can describe it as a shirt sleeves environment. But then the other sort of mission we'd be thinking of is another orbiter, and that would be a radar orbiter, because the problem with looking for active volcanism on Venus is that the surface is completely hidden from view by this cloud cover which encircles the planet. But if we use radar, then you can see through the clouds, and so we would try to see the surface change. We would try to see the morphology around volcanoes change as new lava flows are detected and so on. So that's probably our best hope for detecting active volcanism, and that'd be quite exciting.
I think another one for you, Colin, a related question from Aaron Gormley via Twitter. Is a Venus rover ever going to be a possibility?
There are proposals for Venus rovers. Unfortunately, it would be a very expensive mission, because getting anything to operate down at the surface of Venus where it's 450 degrees centigrade is really difficult, because standard electronics don't work at that kind of temperature, because not only do the silicon components don't work, but also things like soldered connections that would melt. So probably most of your electronics would have to be in a cooled container, a cooled compartment. So how do you cool that? Well, you'd probably need some sort of air conditioner, cooling system. How do you power that? Because one of the frustrating things is that although Venus is close to the sun and you've got very bright sunlight at the cloud tops, once you're down at the surface, only about 1% of the sunlight reaches the surface, so it's too dim for solar panels. So then you have to take a nuclear power system and dump heat out into this environment, which is 450 degrees. So it very rapidly becomes a multi-billion-dollar or multi-billion-euro mission, which I don't think we're about to do in Europe. And
another question about the aerobraking this time, maybe one for Patrick, from Michael A on G+. Why have we not tried to break the previous record of aerobraking depth? Why only 130 or 129 kilometers? And also a follow-up question, is it to do with the entering angle, or would the spacecraft be destroyed even sooner if you did that?
Well, one of the reasons, of course, is that we are trying to continue the mission after this experimental aerobraking, so we don't want to take too many risks that would damage the spacecraft. What was the other part of the question?
The other part was related to the angle of entry, or maybe that was the part you answered.
That might be for Adam, this one.
Okay.
Yeah, okay. I mean, I'm not sure about the angle exactly, but essentially, the lower you go, the hotter and the more intense the environment is. So it was decided that we would be targeting a particular level of pressure in order to gather some scientific results, and so we've governed our operations to meet that target. So in fact, I didn't explain earlier, but we've been actually pushing the orbit lower 3 or 4 times in the last few weeks in order to get to a higher pressure, dynamic pressure, and hence to meet these targets. So once we've met the scientific goals, then we don't go any lower just for the sake of it.
Okay. And Håkan, you had something?
Yeah, actually, when you talk about the angle of attack for a spacecraft like that, it's more when you're doing a real entry into the aero capture, actually, into the atmosphere, what you do with a probe that's going to stay in the atmosphere. So maybe that's what this person is questioning. In our case, we're coming almost tangentially into the atmosphere and just sinking sort of slowly to the altitude we are reaching. But as a matter of fact, we already have a world record on Venus, because nobody else has been so deep as 129 kilometers on Venus before and still being in operation. So only the missions that have disappeared into the atmosphere and then don't work anymore, they managed to do that.
Yes, I was just going to precise that we, in terms of learning from the aerobraking technique, both technically and scientifically, we do not need to go lower than what we have just achieved. So I would say mission success on this aerobraking part, and therefore we hope to now continue by raising the pericenter and do a bit more science for the other instruments of Venus Express.
And that's a nice place to say congratulations for a successful mission again from Masonari Watanabe from Twitter, who also asks, it seems like the air is maybe less dense than you thought. What's the reason? And do you think other parts of Venus's atmosphere are also less dense? Maybe Håkan, you can answer that one.
Yeah, well, one thing is that we are now looking at a latitude which is quite far north. We are approximately 75 degrees north. And the models we have are based on data taken by spacecraft at lower latitudes. So that is one aspect. And also the solar, the phase of the solar cycle now is not very active. So that's also a reason why the density of the atmosphere at this altitude is less than it would have been in another case.
And you've got differences also between day and night side.
Yeah.
How does the orbit of the aerobraking change with the?
Yes, this is a significant difference, and that one has turned out to be more important than we thought, because when we are crossing the line between the night and the day, the so-called terminator line, we see a dramatic change over just a few hundred kilometers. We can see how the density at the same altitude changes really very much, with a factor of maybe 4 or 5. Even.
Okay. And there was another question about the orbits of Venus Express. Here it is from G+, from Claudio Tanzanelli again. Why is the Venus Express orbit so highly elliptical? Why isn't it circular like, for example, other probes around Mars? And are there maybe advantages of this? Does Patrick or Adam want to take this one?
Well, I can say something about this. Because different kinds of science investigations really demand different kinds of orbits. So if your mission is focused on radar mapping or high-resolution surface imagery, then you always want to be at a low altitude all the time. But for example, if you want to see how the magnetic fields and the ionosphere of the planet interact with the environment and with the solar wind and so on, which is one of the goals of Venus Express, then it's very useful to have this orbit which changes in altitude all the time. So Venus Express can be as low as 130 kilometers above the surface, or it can be as high as 66,000 kilometers above the surface. So that's really good for that kind of investigation. The other thing also is for the imaging investigations. We can get high-resolution images of the clouds and studies of the clouds when we're close, but when we're far from the planet, we can get a view of the whole southern hemisphere at once, and that's been really great for looking at the south polar vortex. If you haven't seen pictures yet, which Venus Express has taken of the south polar vortex of Venus, go and look them up now because they're beautiful, and we get those big views because we were high above the south pole of Venus. So that there were advantages to the elliptic orbit.
Yeah, there are absolutely very good reasons that Colin mentioned here. But there's also a very practical reason that the spacecraft of Venus Express is not able to get into an orbit which would have been circular, because Venus is a very heavy planet. It takes a lot of energy to go down to a circular orbit. If you take the sister spacecraft, Mars Express, around Mars, is able to go to a much lower orbit just because Mars is a much smaller planet, it's less heavy, and therefore it's easier to go down.
I want to go back to Colin and ask him some more about the vortex. How does it compare with hurricanes on Earth, for example?
The vortex on Venus, the polar vortex on Venus, is basically caused by all this air heated at low latitudes near the equator where the sunlight is strongest, which then moves away from that region of heating towards the poles, and then it all swirls into this enormous vortex, very much like what you get in a sink when you pull out the plug. So this vortex on Venus, the core of the vortex, this bright feature, which you can see in the pictures, can be about 2,000 kilometers across, typically, which is much bigger by over an order of magnitude than hurricanes on Earth. So although it shares some similarities in how it looks with these spiral arms, it's over 10 times bigger.
And a question just popped up related to the circular orbit or elliptical orbit discussion from Kevin Burns. He said, suppose Venus Express was prepared to go into a circular orbit with regards to fuel, heat, shielding, etc. How many passes would it have taken it beyond the 3,000th? Like, what would its lifetime be if it was possible to do that?
Yeah, well, in time it probably would be quite similar. Well, actually, it could be a bit longer because the reason we are running out of fuel now is that we need to keep our pericenter high, that it doesn't go into the atmosphere. But if we had a circular orbit, that effect would have been much less. We could have lived a much longer life, similar to perhaps what Mars Express does. We're talking about the number of orbits, of course. As Venus is approximately as large as the Earth, we know that an orbit around the Earth takes typically something between 90 and 100 minutes. So then you can see that you get maybe 15 orbits per day or something like that. And now instead of one, so we would have done 3,000 times 15, so 45,000 orbits instead.
A question from Twitter. I think this is probably one for Adam, from Elisabetta Bonora from Italy. She wants to know about the communications that Venus Express has with Earth. Will communications be more frequent with the Earth during the aerobraking? And maybe you can talk about the downlink of the data as well.
Yes. So we use a large antenna on the spacecraft, which we point to the Earth because we're a very long way away. And during aerobraking, actually, we've tried to make sure we usually uplink from a ground station in Spain, and we also receive the data from aerobraking at that ground station. But to be doubly sure that we can remain in contact with the spacecraft in case there's a problem in Spain, we also booked another ESA ground station in South America. So we have two passes a day, one in Sobreros and one in Malague. And we uplink commands twice a week, and we receive data at those stations every day. And it's quite complicated because since the orbit is changing now the orbital period is more than an hour different each day. Well, the period's not different, but the times things happen is more than an hour different. We can happen that we're actually going through pericenter, where we're in a special attitude and AOCS mode. So our communication passes sometimes get interrupted by the spacecraft operations. So sometimes our passes are split in two, and we have to collect what information we can when we can see the spacecraft.
Thank you. This one's for Colin, from Google again, from Sam Frederick. What are the strengths and weaknesses of having different instruments measuring the surface of Venus in different wavelengths?
Well, you see different things. So, for example, we've mentioned several times that Venus is completely covered in cloud. Well, if you look at Venus in almost any wavelength, certainly visible wavelengths, but also UV and infrared wavelengths, you usually see just cloud. If you want to see the surface, you can go out to radio wavelengths by using radar. So that's what was done by the Magellan orbiter. But we also have a special trick which we can use, which was only discovered in about 1980 or so, by accident by some astronomers on ground who pointed their telescope at Venus because it was just there, and they were looking at some near infrared wavelengths around 1 micron or 1 micron, 1.7 microns, 2 microns. This is in the infrared, the near infrared, and they found that they saw lots of light coming from Venus on the night side, which they weren't expecting. And it turns out that the surface of Venus is so hot that it's thermally emitting infrared light, which normally you wouldn't see because it'd be at longer wavelengths, but because the surface is so hot, it's emitting at these wavelengths. And that actually makes its way through the clouds of Venus because the clouds are so incredibly reflective that the photons from the surface, the light from the surface, bounces off lots of cloud particles and still makes its way out to space. So we can observe that from Earth using telescopes, or we can observe it from Venus and from Venus Express. And Venus Express is in fact the first orbiter at Venus equipped with cameras and spectrometers which can observe Venus at these wavelengths. And so Venus Express, a large part of its science return has been using these special wavelengths where we can study not only the atmosphere above the clouds, but we can study the lower clouds, we can study the composition of the atmosphere below the clouds, and we can even see the surface at some wavelengths. So that's a long answer to a question. The short answer is if we want to see the surface from Venus Express, there are some very specific wavelengths around 1 micron which we can use, and that's about it.
Oh, that's great. And there's a couple of related questions, actually. One from Herath Bernsdorf. What elements occur in the atmosphere? So I guess what's the chemical composition?
So most of the chemical composition of Venus, of the atmosphere, is carbon dioxide, CO2. If you took away the carbon dioxide, so the surface pressure on Venus is about 90 times higher than it is on Earth, and almost all of that is carbon dioxide. If you took out all that carbon dioxide, you'd still be left with the second most abundant gas on Venus. I'm thinking is nitrogen. You have about as much nitrogen in the atmosphere of Venus, roughly the same order of magnitude as you have on Earth. It's just on Venus it's completely dwarfed by the amount of CO2. And after that, then you've got various small chemical, minor chemical constituents like sulfur dioxide, which may come from volcanoes. What you don't have much of is water. There's very, very little water vapor left on Venus. And where it went and when it got lost is one of the main questions on understanding how Venus has ended up the way it is now.
And that's a nice lead into a question that we received earlier on G+, maybe either for Colin or for Håkan. What about the greenhouse effect on Venus? What has Venus Express been doing to study that?
Yeah, of course, that's one of the major things, and in particular very interesting in connection with the situation on the Earth. And as Colin said, it's by far dominated by CO2 in the atmosphere. So there's a very strong greenhouse effect. Venus is really the queen of greenhouse effect in the solar system, one can say. Now, of course, planets do need some greenhouse effect, at least the Earth. I mean, if we didn't have the greenhouse effect on the Earth, it would be really far too cold to live here. Now, on the other hand, on Venus, it has become very much too much, making it so hot. So it's very effective there. And if we wouldn't have the greenhouse effect on Venus, we would have definitely a much lower temperature. I don't remember out of my head how much it would be, but more than 100 degrees less, in fact.
Well, if I could just add, I mean, one of the paradoxes about the Venus greenhouse effect, we think that you look at these 3 planets, Mars, Earth, and Venus, and you expect them to be similar, and then you think, well, Mars is further from the Sun, Venus is closer to the Sun, so of course Venus is hot, Mars is cold. But actually, Venus absorbs less sunlight than Earth does. Although it's closer to the Sun, it's so reflective that most of the sunlight arriving at Venus is reflected away. So the cloud top temperatures on Venus are actually colder than they are on Earth. But then the surface is so much hotter because of this enormous greenhouse effect. So in fact, the greenhouse effect was understood at Venus. I was going to say earlier than it was on Earth, but certainly they really understood and proved that the greenhouse effect worked on Venus because there's so much carbon dioxide, and that explained why it was so hot. And in fact, several Venus scientists have gone on from studying the greenhouse effect on Venus to then being experts at studying it on Earth. And it's great to compare the planets like that.
And that's just really interesting, this point about the clouds, because it really shows how important the clouds are in this whole concept of the thermal balance of planets. The greenhouse effect versus the cloud effect is very important interplay between the two.
We'll come back to that topic, I think, but there's a question here for Adam again from Twitter from Icarus Factor. Is Venus Express part of a deep space network to get the data, or is it a direct link?
Well, ESA has its own deep space network. We have 3 ground stations in, as I say, Spain, South America, and in Australia. We also make use of the NASA's Deep Space Network, but we're not a relay like Mars Express is sometimes to other spacecraft. So we're not a communications point, no.
And back to the atmosphere. So I think this one is for Håkan. How does Venus's slow rotation affect its atmosphere, or maybe also the other way around?
That's a very good question, which we don't really have the answer to. The rotation rate not only is going very slowly, but it's going backwards with respect to the other planets. And exactly why that is the fact, we don't know. But we do know that the atmosphere itself is rotating very, very quickly around the planet. And at the top of the cloud layer, as I said in the beginning, we have really hurricane forces wind. And then gradually towards the surface gets less and less, and down at the surface, just because of the very dense atmosphere there, it's only a few meters per second, perhaps at the most. So we have a large variation depending on the altitude and also depending on the latitude, on the winds and the rotation of the atmosphere. But exactly how it couples to the rotation of the planet is not known. We do study these things because we have models, so-called general circulation models, where we try to explain how the atmosphere is behaving and moving through on the global level. And there we also connect the motion of the planet and see, for example, how mountain ranges is sort of trying to pull the atmosphere with it, and also generate waves propagating upwards. We also can see these waves on the top of the clouds, and we can see them as a function of altitude and other type of measurements we make in the temperature measurements. So it's a very complex interplay between the surface and the atmosphere that we really need to study even more to understand better.
And does it have a net effect of either speeding up the atmosphere or slowing down the planet's rotation over time, do you think?
That's a good question. And the particular thing is that we have seen since the time of Magellan, where we had very precise measurements of the rotation rate of Venus, of the solid planet, and we look at it what it is now, we've seen that it has changed since then. It looks like the planet has slowed down while the atmosphere has speeded up. And then, of course, one can immediately think, is that a sort of a transfer of rotation and momentum from the solid planet up to the atmosphere, or is it because of something else, or is it just a coincidence that this happens? So we can't tell that now, but it is certainly an interesting area to study.
Mm. And another interesting area is related to magnetic fields. On G+, Sarah Tuttle asks, does Venus have a magnetosphere? Is it strong enough to be indicative of a large metallic core?
That's another good question. We have a very large magnetosphere around Venus. If you think about that, Venus itself does not have an interior magnetic field. It needs us, not as we have been able to tell. We're trying to see that now we're doing the aerobraking measurements. We're going very deep down to try to see if we really can find a trace of a magnetic field from the planet itself. But we haven't got any solid evidence for that yet. But we have seen, of course, this huge magnetosphere that is built up by interaction of the solar wind that is blowing against the upper atmosphere and then deflected by the atmosphere. And because those particles are charged, they set up an artificial magnetic field around the planet. So it appears as a magnetosphere, just like us around other planets, but of course it's much, much smaller than one of the Earth, for example. Because the Earth has a really substantial magnetic field that we don't see at all on Venus.
And this question nicely links atmosphere to aerobraking again from Michael I. Will the Venus reference atmosphere models be improved by what we learn from aerobraking? Maybe Colin or Håkan wants to take on. Colin?
Well, in fact, this process is ongoing now. The reference atmospheres which engineers, for example, use if they're designing Venus exploration missions, the standard international reference atmosphere for Venus dates back from 1985, and it's partly a reflection that there haven't been many Venus missions since then, particularly those studying the atmosphere. I mean, the last Venus mission before Venus Express was the Magellan radar mission launched in '89. So Venus Express really reflects a return to Venus by the international science community. And yes, now that the Venus Express mission is approaching its end, although the science analysis is, of course, ongoing, the science community is turning their attention to producing a new reference atmosphere. And it's a big work because we have lots of individual measurements of velocities, densities, compositions, and things like that, and we need to try to distill that down into a set of chapters and descriptive papers and tables. But that work is ongoing, and we shall see the results within a couple of years, I'd say.
So if Venus Express doesn't make it back up to the top of the atmosphere in the next 15 days, how long will the science data archives keep you busy for, do you think?
Well, that's a question for the funding agencies rather than the scientists. I mean, there are terabytes of data for us to analyze, so certainly no shortage of data.
A question here from Tobias Terrier. During the Apollo missions, uneven lunar mass concentrations caused unexpectedly high variations in orbital altitude above the ground. Is this a cause of uncertainty for Venus Express? Is the gravity field known well?
The gravity field is actually known quite well on Venus. Magellan did a very good job there. After its radar mapping part, it spent a bit more than a year actually after it had done some aerobraking to get down into a lower circular orbit to do very good mapping of the gravity field of Venus. There are a few places which are less well characterized, and that's something that could be improved, but there are definitely also similar mass cons on Venus as there are on the Moon, but not anything that to any large extent affects the orbit in a way that we need to compensate for it. But sometimes we do notice these effects.
Yeah. There's a couple of fun questions here about terraforming. So could you use the gases in Venus's atmosphere to terraform it? Colin, do you want to take that question?
Sure. Because terraforming Earth, this is what we're effectively trying to do with legislation to change carbon dioxide emissions and things like this. You could also say trying to fix the ozone hole by regulating green CFCs. This is terraforming. We are shaping our environment, and you can see how difficult it is to do here on Earth, where we have all our industry here. If we want to produce tons of some gas, we've got all our industry to do it. It's already difficult enough on Earth. After Earth, terraforming Mars is already a daunting prospect. And now the atmosphere of Mars is more than 100 times less massive than that of Earth. So that's perhaps a starter planet for terraforming. But to then go from there to Venus, you're talking about an atmosphere which is more than 1,000 times more massive than that of Mars, is just another prospect altogether. So incredibly difficult. Come back and ask me the question once you've succeeded in terraforming Mars.
Back to some aerobraking questions. What kind of sensors are used in order to perform the measurements and the observations? And that question comes from Christian Timote. Adam, do you want to take that question, please?
Sorry, Emily, could you repeat it, please? I just had an operational question. Yeah, do you hear me, Emily?
I'm sorry. What type of sensors do you use in order to take measurements during the aerobraking?
Okay.
So, for example, pressures and temperatures. Okay.
Well, we have some accelerometers which measure the acceleration. We have various thermistors that measure the temperature, and then we derive some other information from those measurements.
And also another question from from Don Merritt. With the highly elliptical orbit, how much does the apocenter altitude change due to the aerobraking?
That's a tricky flight dynamics question that I feared somebody might ask me, and I'm afraid I don't know the answer at the moment, but I can find out for you.
But I just did a calculation on this because I saw the question arose somewhere else, and so while we were in a 24-hour orbit before aerobraking, the apocenter altitude is about 66,000 kilometers. And if my undergraduate application of Kepler's laws of planetary motion were well done, then I think the apocenter altitude is going to come down to about 60,000 kilometers. So from 66,000 kilometers down to about 60,000 kilometers. But I can follow that up with Don later.
So it's not just the pericenter, but also the apicenter that's changing during this whole aerobraking campaign.
Yeah.
Yeah, because as Adam said in his introductory remarks, aerobraking is used for mission planning to circularize an orbit, which means you're reducing the apicenter altitude so that the orbit becomes more and more circular. And we're seeing a small version of that in our own mission.
And we mentioned earlier, we were talking about atmospheric pressures and how it would be very difficult to send a lander to the surface, for example. Jürgen from G+ also asks, why is the atmospheric pressure on the ground so extreme in the first place? Håkan?
Yeah, we think that the way how it was going, that in the very early days of Venus, it was very similar to the Earth. Maybe the pressure was not too much higher, but still Venus was close to the sun, and then eventually we started cooking out the water vapor from the oceans, and that of course was driving the greenhouse even more, because water vapor is a very strong greenhouse gas. And eventually we had been cooking out all the water into the atmosphere, and then there was no thermostat anymore, so the temperature could rise. And then eventually we started to cook out also carbon dioxide from the carbonate rocks. And of course there's a lot of carbonate rocks. You can get a lot of carbon dioxide out in the atmosphere, and then you get this runaway greenhouse effect, as we call it. The temperature is just rising and rising, and that's basically where we are now, we think.
I could say, if I could just make another remark there, you could also ask the question, why isn't the pressure higher on Earth? Because initially, when the surface was really hot, when you had a molten magma ocean, which we think is what happened in the early formation of these planets, you probably had high pressure atmospheres on all the planets, and it's partly only when the planets then cooled down that the atmospheric pressure came down. So why is it that we managed to get all the CO2 out of the atmosphere on Earth? And the answer is partly it's because reactions with water managed to lock it up in these carbonate rocks. But so perhaps Earth is the anomaly rather than Venus.
And I think that's a nice point to maybe start wrapping up and hearing some final messages from each of you. Adam, I'd like to ask you first of all, what lessons have you most learned from this aerobraking phase that might help with future operations for other missions, for example?
I think the thing which has struck me most is the interaction between doing an aerobraking passage, measuring what's happened, and then deciding what to do about it next. And that cycle is we've discovered that's quite a long cycle. It looked, when we were getting ready for this, that we had quite a reasonable turnaround. But in fact, actually, that whole control loop for us to be able to react to what's happening in the atmosphere, for us, is quite a long loop. And so to do a big aerobraking campaign, you'd need to think about how to shorten that control loop. And
Colin, what would you say is the biggest science highlight for you out of the whole mission, either during the aerobraking phase or perhaps in the whole 8 years?
Well, I think probably the most exciting science thing we've been trying to chase with Venus Express is this question of active volcanism now. Are the volcanoes, which we know exist on the surface of Venus from the radar maps, are they active? And we've been tracking sulfur dioxide levels in the atmosphere. We've been hunting for different minerals at the surface, dark rocks near volcanoes. We've been hunting for bright spots. But that's what we're hunting in terms of what Venus is like now. In the longer term, probably the big picture we're trying to chase with Venus Express, but then also future Venus missions, is to understand how this question of why is Earth not more like Venus, which is a more sort of normal state for us to find planets in, and this suddenly becomes very relevant in an era where we're discovering lots of terrestrial planets around other stars. I mean, every month you open a newspaper and find a report of another Earth-sized planet being discovered around another star, and when is an Earth-sized planet actually going to be Earth-like and habitable and so on? Is it enough for it just to be Earth-sized? And studying Venus helps us figure out, not all Earth-sized planets are are nice to live on.
And this is kind of related actually to a question that's just come in. What other ESA missions might we expect in the future to explore the inner planets? Maybe not just Venus, but maybe even exoplanets one day.
Well, there have been one recently selected ESA mission will be searching for exoplanets, terrestrial-sized exoplanets, in much greater numbers than ever before. And so that's a detection mission which will detect these exoplanets and find out how many of them there are and where they are. But then other missions on the drawing boards would then not just detect them, but then take the spectra of light passing through their atmospheres so that we could tell which of them have, for example, water in their atmosphere, which is a pretty key species for us. But then also things like ozone and carbon dioxide, so we can then try to understand which of them might be Earth-like or Venus-like or something else.
So we're hunting for other Earths and also other Venuses and maybe whole other solar systems as well.
Yeah.
Håkan, Colin touched on this a little bit already, but what do you think the Venus Express mission has taught us most about Earth?
Yeah, that's a good question. I think about the Earth, it's of course hard to say that you directly derive information about the Earth, but I think that by similarities there are many things one can learn. And one really need to understand Venus to be able to understand the Earth, one can say, in particular because they are so similar in size. But also Mars. So if you take all the three planets together, you really need to be able to understand how all these planets work together to be able to tell more about how the Earth works in detail. Of course, then we have a lot of processes that we can tell that we have both on Venus and on the Earth. For example, the interaction with the solar wind, we have put quite a lot of emphasis on our measurements of that. We measure magnetic fields, measure energetic particles in the magnetosphere. We see how that compares to the Earth. We see how material and fractions of gases, atoms and ions disappear from the upper part of the planet. We have that on the Earth and we have it on Venus at a similar magnitude, which is a bit surprising because, as I said before, the magnetosphere on Venus is much smaller than the one on the Earth, but the amount of mass which is disappearing from Venus is approximately the same as that of the Earth, and that is somewhat surprising. That's something else one can say that we have really learned now from Venus Express that is also applicable on the Earth. So these processes that are similar but still different on the two planets. Then of course we are studying quite some extent the cloud and cloud formations. Now the clouds on Venus are made up out of droplets of sulfuric acid, concentrated sulfuric acid, and a little bit of water, at least the upper cloud layers. The lower cloud layers we don't really know what they are composed of. But the process of formation and dissolution of clouds, of course, is something we are studying too. That also applies to the Earth.
Okay. And finally, Patrick, what do you hope that people will remember most about the Venus Express mission?
Well, of course, one of the obvious answer to this is that Venus Express has been a great mission over the past 8 years and continues to be a great mission, of course. So I would hope that people will remember the great wealth of scientific data and discoveries that have been compiled over the last 8 years or so, and even the future ones now. As you know, there is a new Venus book in preparation, and this will greatly record the knowledge of this mission in the next years or so after the publication. But of course, now that we are concluding Aerobraking, I would hope that people will remember Venus Express as the first ESA spacecraft to conclude a period of aerobraking around the planet in our solar system. So this is to me one of the great achievements of this mission.
Thanks, Patrick, and thanks to everybody for joining today during such a busy time during the last week of aerobraking. I'm sure that you're very busy also preparing for the next 2 weeks of raising the spacecraft's orbit. Thank you also to everyone who joined to watch today and for asking questions. This Hangout will be archived, of course, in the ESA G+ page and also on YouTube, youtube.com/ESA. For Venus Express, you can find out more by looking at esa.int/Venus Express. You can also follow the progress of the Aerobraking campaign via the Rocket Science blog and via ESA Operations on Twitter. And to stay tuned for more ESA Hangouts on a whole range of topics, then you can connect with us on a whole range of our social media websites via esa.int/connect with us. Thanks again to everybody for joining. I'm Emily Baldwin.